In this exercise, we wish to find the area of a region R, enclosed by a parametric curve. On the top of the page, we can see the parametric curve R, of t, with t, between 0 and 2 pi. The graph of the curve is given, although it is not necessary for our goal. As we can see, the given region R, is enclosed by a parameterized curve. Greens theorem is a very handy and popular method for calculating the area of a region, enclosed by a simple, closed, curve C of the plane, as long as the region R, it encloses, satisfy the hypotheses of Greens theorem. Which are: let R be a simply connected plane region whose boundary is a simple, closed, piecewise smooth curve C oriented counterclockwise. If f, x, y, and g, x, y, are continuous and have continuous first partial derivatives on some open set containing R, then. And below we can see Greens theorem representation. Now some clarifications, as to Greens theorem representation. Vector capital F equals f, x, y, comma, g, x, y, represents a vector function, vector field, extended throughout the region R. The line integral of the dot product of vector f, with the differential dr, is considered over the closed curve C, which is parameterized, as we can see, with R, t, equals phi, t, delta, t, and t takes values between t1 and t2. But from the definition of a line integral of a vector field f along a piecewise smooth curve C, that encloses region R, in the direction of parameterization R of curve C, is defined as, and below we can see the definition, which goes like that. The line integral of the dot product of a vector field capital F, with the differential of a parameterization R, of curve C, over the curve C, equals with the line integral, as to t, over the domain t1, t2, of the product of f of R of t, with the derivative of R. R of t, defined on the domain, t1, t2, is a regular parameterization, that is the magnitude of the derivative of R as to t, is not zero in the above domain. Now general speaking, and trying to establish a method. If we have first, a vector f equals f, x, y, comma, g, x, y, that represents a vector function, vector field, of the plane, extended throughout a simply connected plane region R. Second, R, of t equals phi, t, delta, t. T, between t1 and t2, represents the boundary of region R, and is a simple, closed, piecewise smooth curve of the plane, oriented counterclockwise. Then what are the steps one should follow, in order to calculate the above line integral? One first has to calculate the function composition of f, and R. The new vector function, now is defined as to t. Also, the derivative of R, is required. By continuing the operations, it occurs that, the dot product, of f, of R, of t, with the derivative of R of t, is a real function of t, with t, between t1 and t2. Now going back to line integral sigma, by substituting we get a line integral of a real function of t. As we are going to demonstrate later, this line integral is our tool in order to calculate the area of the region R. Below we can see the composition of some vector field f, with the given parametric curve R. So now the question that arises is what the vector field is. This question is to be answered in the next few steps. Now as we can see, Greens theorem connects a double integral, with a line integral. Below we can see again the formula. From this, by using the previous outcome, we get the formula. This formula is easily executable, at least as to the first part. It's a line integral as to t. But we still have to clarify some parts of the double integral of the second part. On the other hand, we know that the area of a region R is given by a double integral. This double integral is calculated over the region R, and A represents the area of region R. So somehow, we have to find a way to connect these double integrals. And by connecting them, we mean to find proper formulas for f and g, such that partial derivative of g, as to x, minus partial derivative of f, as to y, equals 1. And by doing this, we shall have found a way to pass from a double integral, most times very hard to deal with, to a line integral, mostly easier to deal with. The most common formulas for functions f and g are. As we can clearly see, the first two can be used to delete one of f, or g, if one of them is of a rather complicated form. The third one permits deletes, or factorization, of terms. So we can use the one that is most convenient for us. So now recapitulating, if a curve C of the plane, with parametric form R of t, with t, between t1, t2, satisfies the hypotheses of Greens' theorem, in order to find the area of the region R it encloses, we follow the steps. We firstly calculate the dot product of f, of R, of t, with the derivative of R. Where f is one of the standard choices of the previous page. The area is calculated by using the integral below. Below, we can see the parameterized curve R, of t, which is the boundary of region R. Now let us check out if it is a simple, closed, piecewise smooth, curve C, oriented counterclockwise, as Greens' theorem demands. First, curve R is obviously smooth. Since a, the component functions, are one of t equals sine 2t minus 2 sine t, and are 2 of t equals 2 cosine t minus sine 2t of the curve R of t, are continuously differentiable within the interval 0 to pi. b. There is no t within 0 and 2 pi, such that R1 t equals R2 t equals 0, except, maybe, the end points. Second, curve R is also closed, since R, 0, equals R, 2 pi. And below we can see the proof of that. R of 0 equal to sine 0 minus 2 sine 0, 2 cosine 0 minus sine 0 equals 0, 2. R of 2 pi equals sine 4 pi minus 2 sine 2 pi, 2 cosine 2 pi minus sine 4 pi equals 0, 2. Third, curve R is a simple one since, as we can very easily see, if s less than t and R of s equal to R of t, then s equals 0 and t equals 2 pi. Thus, the parametrization starts and ends at the same point but otherwise does not intersect itself. At last we have to indicate the orientation of the boundary C. The easiest way to do this is, maybe, by choosing a few points onto the curve R, of t. The first step is to take into account the interval over which R, of t, is defined. In our case 0 less than or equal to t less than or equal to 2 pi. So we fill in a table of points onto curve R, giving t some values. The parameter t determines the position of a point on the curve, as it moves along the curve. Now as t receives continually increasing values, between 0 and 2 pi, the above point travels along the curve. This movement defines an orientation or direction of the curve. In our case it's very clear that the point moves counterclockwise. Another way to determine the orientation of a curve is by using the unit tangent vector of the curve. At each point on the curve, the unit tangent vector points in the direction of increasing parameter value. That is, the direction of motion, as t increases. By calculating and visualizing the unit tangent vector at various points, we can see how the curve curves and bends, revealing its overall direction. For the moment, we stop here and we will present the above method in another example. Now, since all conditions of Greens' theorem are satisfied, let us proceed to calculate the area of region R. We firstly choose as f, vector function 0, x. Now, since the parametric curve R is given, we can proceed and calculate the dot product of f, of R, of t, with the derivative of R. As we can see, the outcome is a real function of t. The line integral of this dot product will give us the area of region R. Below we can see the illustration of the line integral and the outcome of the integration. Now some very basic notations follow. First, can Greens theorem applied if curve C is not completely smooth? Yes, Greens theorem can still be applied to find the area enclosed by a curve, even if the curve is not completely smooth, as long as it is piecewise smooth and closed. This means the curve can have corners or sharp edges, but it must be made up of a finite number of smooth pieces joined together. Second, can Greens theorem applied if curve C is not simple? No, Greens theorem, in its basic form, cannot be directly applied to find the area if the curve is not simple and closed. But if the non-simple curve encloses a region that can be divided into multiple simple, closed regions, Greens theorem can be applied to each of those smaller regions, and the results can be combined, added up. Can Greens theorem applied if curve C is not closed? No, Greens theorem cannot be directly applied to find the area if the curve is not closed. If the curve is not closed, there is no region R. In other cases we generally can use Greens theorem if the curve is open. We must first close the curve by adding a line segment to connect the endpoints. But as to area calculation, if the curve is not closed, Greens theorem cannot be used directly for area calculation.